What if I told you that the difference between a sweet smell and a rotten one could be down to the arrangement of atoms? Welcome to the fascinating world of stereochemistry. Stereochemistry, in its simplest terms, is the study of how atoms and molecules are arranged in three-dimensional space. It's a crucial aspect of chemistry that dictates how molecules interact with each other and how they behave in biological systems. Stereochemistry can be the difference between a medicine being a lifesaver or a poison. For instance, one arrangement of atoms can create a sweet-smelling molecule, while a different arrangement of the same atoms can create a molecule with a rotten smell. This is the significance of stereochemistry in biological activity. Stereochemistry is a vast field, encompassing concepts like stereoisomerism, geometrical isomerism, optical isomerism, chirality, and much more. So, get ready to delve into the microscopic world of molecules and their spatial arrangement. Stereoisomerism is like the twins in chemistry, identical yet different. This fascinating concept revolves around how the same atoms can connect in the same sequence, but still form distinctly different compounds. The magic lies in the three-dimensional orientation of these atoms, a feature that gives birth to what we call stereoisomers. Now, stereoisomerism branches out into two primary types: geometrical isomerism and optical isomerism. Let's dive into each one of them. Geometrical isomerism, sometimes referred to as cis-trans isomerism, is all about the spatial arrangement around a rigid bond. That could be a double bond or a ring structure. Think of it like seats in a theater. You and your friend could be sitting next to each other or one behind the other. You're still in the same theater watching the same movie, but your perspectives are different. That's the essence of geometrical isomerism. On the flip side, we have optical isomerism. This phenomenon occurs when compounds, called optical isomers or enantiomers, mirror each other but cannot be superimposed. It's like your left and right hands. They're mirror images, yes, but try as you might, you can't overlay them to match perfectly. They're non-superimposable mirror images. This characteristic of optical isomers gives them their unique ability to rotate plane polarized light in different directions, hence the name optical. Both these types of isomerism play a crucial role in the biological world. From the structure of DNA to the function of proteins, the orientation of atoms matters. It's like a lock and key mechanism, where even a slight alteration in the structure can prevent the key, in this case a molecule, from fitting into its lock, or the receptor site on a cell. So, as you see, even the smallest shift in atom arrangement can create a whole new compound. It's an incredible testament to the beauty and complexity of the world of chemistry. Now that we know what stereoisomers are, let's get to know them by their names. The E and AMP-Z nomenclature is one way we identify different types of stereoisomers. The letters E and Z come from the German words entgegen and zusammen, meaning opposite and together, respectively. This system of nomenclature is used to distinguish between different geometric isomers, particularly in cases of alkenes. When the higher priority groups are on opposite sides, we refer to it as E isomer, and when they are on the same side, it's a Z isomer. Now let's turn our attention to the Fischer representation, named after the German chemist Emil Fischer. This method is particularly useful in representing molecules with multiple chiral centers. In a Fischer projection, horizontal lines represent bonds coming out of the plane towards you, while vertical lines represent bonds going into the plane away from you. Next, let's explore the R and AMP-S nomenclatures. This system, developed by Robert S. Kahn, Sir Christopher Ingold, and Vladimir Prelog, is used to denote the absolute configuration of chiral molecules. If you imagine yourself looking down at a molecule, and the priority groups decrease in order from 1 to 4 in a clockwise direction, the molecule is termed as R, derived from the Latin rectus. If they decrease in an anti-clockwise direction, it's an S configuration, from the Latin sinister. Finally, to visualize the spatial orientation of atoms in a molecule, we use the Newman and Sawhorse representations. The Newman projection allows us to look straight down a particular bond and understand the rotational conformations, while the Sawhorse projection gives us a sideways view of the molecule, offering a detailed perspective on the spatial arrangement of atoms. Remember, Knowing their names is just the beginning of understanding their behavior. We'll delve deeper into these intriguing aspects of stereochemistry in the upcoming scenes. So stick around, because we're just getting started. Ever looked at your hands and realized how similar yet non-superimposable they are? That's chirality for you. Now imagine a molecule in your hand. Not all molecules, but some special ones have this unique property called chirality. Named after the Greek word for hand, chair, chirality is a property of an object which is not superimposable on its mirror image. Picture your hands again. They mirror each other but can never be perfectly overlaid. In the molecular world, chirality plays a crucial role in stereochemistry. Molecules that are chiral are often referred to as stereoisomers. They share the same molecular formula, the same bond connectivity, but differ in the spatial arrangement of atoms. And this difference can lead to entirely different chemical behaviors. For example, one chiral form of a molecule might smell like oranges while its mirror image might smell like lemons. Now, let's dive into diastereomerism. Diastereomers are a type of stereoisomer, but they're not mirror images of each other. Picture two objects that are similar but not mirror images, like a pair of shoes. In other words, if a molecule has two or more stereocenters and is not a mirror image, it's a diastereomer. Diastereomers may share many physical properties but can exhibit different chemical reactivity. This difference often comes into play in the world of medicinal chemistry, where one diastereomer of a drug might be therapeutically beneficial, while another could be harmful. In essence, chirality is about mirror images that can't be superimposed, like your hands. Diastereomerism, on the other hand, is about molecules that are similar but not mirror images, like a pair of shoes. Both concepts are key to understanding how molecules behave and interact in the world around us, from the fragrance of an orange to the effect of a drug on our bodies. So chirality and diastereomerism, while related, offer unique perspectives on molecule behavior. Imagine a dancer constantly in motion changing poses. That's a molecule for you in the world of conformational isomerism. Conformational isomerism is a fascinating aspect of stereochemistry. It's all about the different spatial arrangements a molecule can adopt due to the rotation around single bonds. Unlike other forms of isomerism, it doesn't involve breaking any bonds. It's a bit like our dancer, who can extend an arm, bend a knee, or twirl, all without disconnecting any limbs. Let's dive into ethane and N-butane. With ethane, a simple molecule comprised of 2 carbon atoms and 6 hydrogen atoms, the rotation around the carbon-carbon bond gives rise to different conformations. The most stable of these is the staggered conformation, where the hydrogen atoms are as far apart from each other as possible. On the other hand, the eclipsed conformation, where the hydrogen atoms are directly in line with each other, is less stable due to the electron repulsion. In the case of N-butane, we see a similar dance, with the staggered conformation being more stable than the eclipsed one. However, N-butane has 2 types of staggered conformations, the anti and the gauche. The anti-conformation, where the 2 methyl groups are opposite each other, is more stable due to fewer steric interactions. Moving on to cyclohexane, a 6-membered ring, things get a bit more complex. The molecule prefers to adopt a puckered chair conformation, which minimizes the strain and allows for a staggered arrangement of all bonds. Monoalkyl and dialkyl cyclohexanes, on the other hand, undergo a fascinating process known as ring flipping, wherein they oscillate between 2 chair conformations. So, conformational isomerism brings the dynamic nature of molecules to light. It's like the grand performance of a ballet dancer, gracefully transitioning from one pose to another, each pose representing a different conformation. And just like a dance, it's all about achieving balance and minimizing strain. So we've journeyed from the basics of stereochemistry to the dynamic dances of molecules. We've delved into the fascinating world of stereoisomerism, where seemingly identical molecules behave so differently due to their spatial arrangement. We've explored the intriguing concept of chirality, where molecules are mirror images of each other, just like our hands. We've navigated through the complex maze of nomenclature, using E and AMP-Z, R and AMP-S systems to precisely describe these molecular structures. Our exploration continued as we ventured into diastereomerism, where the difference in the arrangement of atoms can transform molecules into their non-mirror images. Finally, we dove into the mesmerizing realm of conformational isomerism, witnessing the constant and subtle transformations in the structure of molecules like ethane, N-butane, and cyclohexanes. This voyage through the microscopic world of molecules is indeed a testament to the beauty and complexity of chemistry. I hope this exploration of stereochemistry has given you a new perspective on the microscopic world. Don't forget to subscribe for more because you won't find me later.